Chapter 20-5 talks about the integrator circuit. And yes, we're talking about integration. We're talking about finding the definite integral between 2 points of a function of x with respect to x. Now, when we do this in a voltage circuit, we don't do it with respect to x. We're usually integrating between 2 points, a and b, some voltage as a function of time with respect to time. So we can do mathematical integration with op-amp circuits. How do we do that? At first, this seems rather difficult. Integration appears to be a really complex mathematical concept, and we're trying to put that into a circuit. But integration is actually simpler than it first appears. So let's take, for example, that I've got a flow rate. I've got water flowing through a pipe, and it's pouring out. And for 5 seconds, it's 5 liters per second. And then for 10 seconds, it goes up to 10 liters per second. And then maybe for 2 seconds, it's back to 5 and then 0. So that's 15, and then this is 17. How would I integrate that over time? Well, integration is finding the area under the curve. So 5 liters for 5 seconds, that's 25 liters. 10 liters per second for 10 seconds, so this area represents 100 liters. So we're at 125. And then this region here, another 5 liters for 2 seconds would be another 10 liters. So the total area under the curve would be 25 plus 100 plus 10. So 135 liters. And how would we do that? How could we sum that up over time with a simple mechanical thing? So here's our pipe pouring out the different flow rates. All we need to do is put a bucket down here and mark the side of the bucket. And after 17 seconds, it would be up to the level of 135 liters. So this is summing over time. Just pour the stuff into a bucket. Now, the electronic equivalent of a bucket is a capacitor. And if I put charge into a capacitor, which is coulombs, and I can do that using a current source, which is creating coulombs per second. If I put coulombs or current into a capacitor, the voltage across the capacitor will rise proportional to its capacitance value. So here I have current as a function of time, and if I go at a steady state of current, so the current is basically a constant value, then the voltage will rise at a constant value. And this is because the current is accumulating within the capacitor, and the capacitor voltage is basically rising like the water in the bucket. And if you recall the formulas for this, there was Q equals CV, where the amount of charge in a capacitor is proportional to its capacitance times its voltage, or we could say that the voltage is equal to Q over C, that the capacitance is basically the thing that relates the amount of charge in a capacitor to the voltage across it. Let's run through the same example as the bucket. So let's do a 1 farad capacitor, and we will put current into that capacitor in amps. So let's say for 5 seconds, I put in a current of 5 amps. And then for 10 seconds, I put in a current of 10 amps. And then for another 2 seconds, I put in a current again of 5 amps. So if I put 5 amps of current in for 5 seconds, then the total amount of charge I will move, since current is amps per second, the total amount of charge that I'll move into that capacitor in this time period here will be 25 coulombs. And then in this time period here, if I do 10 amps for 10 seconds, I'll move 100 coulombs into the capacitor. And then my final thing here, if I do 5 amps for another 2 seconds, So this is 5, 15, 17 total. I will put another 10 coulombs into the capacitor. So after 17 seconds, I will have put 25 plus 100 plus 10. I'll have put 135 coulombs into that capacitor. What will the voltage be across the capacitor? Well, if Q equals CV, then V equals Q over C. And remember, I said that it was 1 farad, so it's 135 over 1. I would have 135 volts, just like I'd have 135 marked on the side of the water tank. So we can use a capacitor to accumulate charge over time to turn that into a voltage which is representative of an integration function. The voltage value is the sum of everything that's happened up to that point in time, resulting in a voltage on the capacitor. So this is how an integrator function is realized in an op-amp circuit. What we do is we put a capacitor in the feedback path where we used to have a resistor. So this is an inverting amplifier because the Vin ultimately goes to the inverting terminal. So if Vin goes up, Vout is going to go down. So we get an out of phase relationship. Now, if Vin goes, let's say, from a 0 value up to some non-zero value such as 1 volt, then what will happen is current will flow into the op-amp circuit. Now, it will not go into the inverting input because it's an open circuit. And this point here is 0 volts. So how much current flows in? The In is equal to Vin over R. So that's what determines the input current. Now that current gets redirected and it ends up going into the capacitor. And this will start charging up the capacitor. So there starts to be a voltage across here. And what the op-amp does in order to hold the negative terminal, the inverting terminal at 0, what has to happen is it has to drop the output to the voltage across the capacitor that results in 0 back at the input terminal. So as soon as we put a step input into the input of that circuit, the voltage across the capacitor will start falling because it's an out of phase relationship. It'll start falling at a constant rate. And that rate is determined by how much current you're putting into the capacitor, how much charge you're accumulating on it, and this causes the voltage across the capacitor to increase. And if we drop back down to 0 at some point, then what will happen is if we're no longer putting charge into the capacitor, then it will freeze its charge value at that value. So at this point in time, basically the voltage will stop rising because we've stopped putting current into it. And so we have accumulated, we have summed up all of the current over time, and now we represent that as a voltage across the capacitor. Now in a world with perfect op-amps, when I put 0 volts on the input here, there will be exactly 0 volts on the output. And then this point will be 0 and this point will be 0. And if everything is exactly 0, I will get no current flowing into or out of the op-amp circuit. But the reality is op-amps are not perfect, even if, let's say, the input here is off by a microvolt. Then in order to adjust that, the output will adjust in order to try and make that 0, and then you'll get a little bit of current flowing into it, which will charge this capacitor up over time. And even if it's a really small amount of current, if it's been sitting there for a couple of days, what will happen is this will slowly drift down to the most negative output or the most positive output, and you will come up to this circuit and you will have plus or minus 15 volts on it. So what you need in an integrator circuit is you need some way to bleed off those non-zero currents so that in its normal state it sits at 0. And that's what this resistor up here is supposed to do, is it's supposed to basically bleed off any little current that results from a non-perfect op-amp, and it keeps the capacitor at 0 until there's a significant voltage that comes in. If there's a big voltage that comes in, let's say from 0 to 1 volt, then this guy will not bleed off that fast, and you'll get the integrated output. So this is one way of doing it, is putting in a bleed resistor. The other way that you can do it is you can put a FET switch across the capacitor, and before you do an integration function, you can pulse that switch, and then you can effectively reset or zero your integrator. So a FET used in this application is essentially used like a switch, and what will happen is we'll pulse this guy here, and it'll click it closed and short it out, and for an instant that'll be shorted, and we'll discharge the cap, and then we'll pop that switch back open, and now we can start integrating what we see on the input. Okay, let's do an example. So let's say I apply a 50 hertz square wave to this integrator circuit. So 50 hertz, that's 10 milliseconds high and 10 milliseconds low for a total period of 20 milliseconds. And let's say it goes up to +1 volts and down to -1 volt. If I apply that square wave to the input of this integrator, what should I get on the output? Now, the way that I usually figure these out is I use the other capacitor formula, which is I of t equals C dV dt. And dV dt is the rate of change of voltage with respect to time. So that's the rise and fall rate of the voltage. And that's what I want to look for. So I'm going to put dV dt out front and say that dV dt is equal to the current going into the capacitor divided by its capacitance. That's how fast the voltage will change. Well, how fast is the current going in, or how much charge we put into this capacitor? The current in is 1 volt, and we'll make this 1K. Basically, the current I'm putting into the capacitor is 1 milliamp. And let's say this is a 1 microfarad capacitor. If I divide that by 1 microfarad, I would get 1,000 volts per second rise and fall rate. So the voltage across that capacitor goes up 1,000 volts per second. And how long do I let it rise? Well, if I'm positive for 10 milliseconds, then it goes negative for 10 milliseconds, and then that would be 10 volts. So the delta V, so the dV dt is delta V over delta T. If the T is 10 milliseconds, that's 1,000 volts per second. So the change in voltage would be equal to the rate of change, the 1,000 volts per second, times the number of seconds, which is 0.01, and that is 10 volts. So the change in voltage would be 10 volts. So when this is high, the output here would fall 10 volts in 1 millisecond. And then when the voltage was negative 1 volts, it would rise 10 volts in 1 millisecond. So you take the input voltage, and from that you figure out the current in going into the capacitor, and from that you get the dV dt, the rate of change of voltage across the capacitor. You multiply that by the change in time, and you're left with the change in voltage, and then you know how fast, or then you know what the total change in voltage is with time, and then you can draw a little sketch of the output. We're putting this in, so it's -1 + 1, -1 + 1. That's what's going in, +1 -1. It has to be centered around 0, because if it wasn't centered around 0, then the charge would accumulate over time in the capacitor, and it would go off to the positive or negative rails. So when it is positive 1, Vout would fall 10 volts. So it would be going from plus 5, it's falling 10, so that would be plus 5 to minus 5. And again, this will also sit around 0, because if it charges up the capacitor too much, it would hit the rails. So it would fall. When this is positive, the voltage would fall 10 volts, and then when this was negative, the voltage would rise 10 volts. And then it would fall 10 volts. And then rise 10 volts. So you're putting in a square wave into the integrator circuit. You're putting in a square wave. Over here. And on the output, you're getting an inverted triangle wave. Now, if you let it charge too long, you'll note that I picked these values so that I would get a triangle wave. If you let this sit too long at a high, then what will happen is that the voltage will fall, until finally it hits like minus 10 volts. It hits the most negative voltage that the op-amp can put out, and then it will stop falling because it can't go any further. So it will basically flatten out at the most negative, and then if I toggle the input, then this will charge up again until it hits the most positive value. So if you don't go fast enough, if the frequency that you're putting in is too slow, then you won't get a triangle wave. You'll get this rise and fall to an upper and lower limit, which is not a square wave, but not a triangle wave either. So you have to balance. If you want to make a square wave to triangle wave generator, you have to run the input square wave fast enough so that the capacitor does not fully charge to the maximum voltage that the op-amp can provide. So the capacitor does not charge to the maximum voltage that the op-amp can provide. So if we have an integrator circuit, can we have a differentiator? And absolutely, yes, we can. If we reverse the resistor and the capacitor, we turn an integrator into a differentiator. And from this, we could, if we had a rising waveform like so, if we put that in, the differentiator would spit out a level which tells you the volts per microsecond, the rate of change of voltage with respect to time. So it would differentiate and find the slope at this point. Now, it's not used as much as the integrator. The integrator has a lot more applications, but one of the things that the differentiator is used for is that when you have a square wave, when a square wave snaps high and low, these points right here are really fast changes, and so the slope approaches infinity. Because if it goes from 0 to 1 in a microsecond, that's 1,000,000 volts per second, and it can do it a lot faster than that. What you'll get out of this is a big spike, trying to say that in this time period here, the slope is minus infinity. It's super fast. And over here, when it goes negative, we would get a very high positive spike. Now, the spikes would be limited by the voltage supply on the op-amp, so it's not going to get anywhere near infinity. But what we're essentially doing is edge detection. We can take a square wave input and we can detect the edges of the square wave, and from that we could trigger events and make things happen. So the differentiator circuit, putting a capacitor in front of an op-amp circuit, is often used to detect the edges of square waves.